All right, so here we are, new semester, and it's time for physics. So, welcome back, everyone. Today, we're going to be talking a little bit more about vectors. Oh, and yeah, don't worry about this big building right here. Today, we want to talk a little bit about a review about vectors, and then we want to talk about how to multiply different kinds of vectors. Well, aloha, everyone. Today, we're going to talk about dot products and cross products as they apply to vectors. All right, so you might remember some things about vectors that we need to have some sort of origin to measure things from. So I'm going to put down this block here. That's going to be my origin. I'm also going to define some directions. That way, towards the towards the library over there, that little jutting out part. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, that way is going to be called my x direction. So I'm going to call this direction positive x. And let's do it this way. All right, and I'm going to label this positive x. That's a pretty good x. All right. So that's going to be my positive x direction to the right. I'm also going to call that way towards the road that I came in on and kind of past those tennis courts here. 5, 6, 7, 8, 9, 10. I'm going to call this my positive y direction. Yeah, that's about right. So if we can get a y over here. Not a great y, but it'll do. All right, so now you can see I have labeled my positive x and my positive y directions. So if I was to count 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, boom. And I wanted to know what is the vector from my origin to over there. You could express this in a couple of different ways. Graphically, it would end up looking something like this. All we do is draw a line from where we started to where we finish. And then the arrow is always on the head, sort of like that. So that would be my graphical version of a vector. If I was to express this mathematically, it would probably be something like 7 in the x direction and 7 in the y direction. So in mathematical terms, we have gone 7 blocks in the x direction and 7 blocks in the y direction. So one way we might express this is if I just call this vector A, I might call this 7 blocks in the x direction. The way we express the x direction is we write an I with a little hat symbol over the top. And we actually call that I hat. Plus 7 blocks in the y direction, we're going to use a J with a little hat over it to express 7 blocks in the y direction. So mathematically, this is a Cartesian way of expressing that vector. This part says 7 blocks in the x direction. If I could write here. And this block over here, this part says 7 blocks in the y direction. Okay, so now that we know that, we have 7 blocks in the x direction, 7 blocks in the y direction, that would be vector A. Pretty straightforward. We could also do this by figuring out how long this vector is and what angle. So if we were to look at it, we had our x direction this way, our y direction this way, and we had a vector that was pointing like this, right? 7 here and 7 there. So when we look at this, we can say, well, obviously this angle right here is going to be a 45-degree angle. If you didn't know that, you could solve that using some trigonometry. You could say 7 this way, 7 that way, and you could express that. And I also can figure out that this, I know from my similar triangles, this is going to be 7 square roots of 2 in length. 7 times the square root of 2. So another way you could express this, it's exactly equivalent. A vector is equal to 7 times the square root of 2 blocks in the at an angle. So a lot of times they'll say at an angle of 45 degrees, or sometimes they'll say it this way, 7 times the square root of 2. And then they do this sort of thing to, not like that, kind of like this, angle. That's not a very good angle symbol. Angle 45 degrees. So either way, any of these ways are equivalent of expressing this vector. So A, that vector can be expressed as 7i hat plus 7j hat, could be expressed as 7 times the square root of 2 at 45 degrees, or it could be 7 times the square root of 2 at 45 degrees, as written over here on the right. Any of those three ways is exactly equivalent. Now, in order to be able to multiply vectors, there are two types of multiplication that we need to know. We have what we call a dot product, which is sometimes called a scalar product. We also have what we call a cross product, or sometimes that's called a vector product. So what does this mean? Well, these are ways of multiplying vectors. If you use a dot product, you can multiply two vectors and get a scalar. That means your end result will not have any direction. If you use a cross product, on the other hand, you will get a vector. That means your end result will have a direction. So let's talk about how to do each of these. So a dot product is actually pretty simple. If you have two vectors and they're expressed, let's start off in Cartesian. So this is a dot product. And we're going to do this in Cartesian form first. So let's say you have two vectors. A vector is going to be equal to, let's make it 3i hat plus 4j hat. And let's make B vector equal to 2i hat plus 5j hat. And we want to know what is the dot product of these two vectors. A dot product, and you'll notice we use a really heavy dot for multiplication here because this is a dot product. A dot B. So we'll say that A dot B or A dot product B when we read that. This is equal to, so here's what we're going to do. We're going to multiply each of the pieces that are in the same direction. So it's a 3 times a 2, and then it's a 4 times a 5, and we're going to add those together. So here it's going to be 3 times 2 plus 4 times 5. This is equal to 3 times 2 is 6, 4 times 5 is 20, so this is 26. You'll notice your answer is a simple number. If we had units on these like meters, we would have meters there too. Actually, we'd have meters squared, which would be a little bit weird, but okay. But really, it's a scalar number. It's very simple. A dot product, all you're going to do is multiply the components that are the same. Let's try it again, make it a little bit harder. A vector is going to be equal to, let's not use A, let's use J vector, capital J, is going to be equal to 2I hat minus 4J hat. And let's make K vector, capital K, is equal to negative 10I hat plus 2J hat. And what happens if we do J vector dot product K vector? So this is going to be equal to, again, we're going to start off by multiplying the pieces that are in the same direction. So it's 2 times negative 10. So 2 times negative 10 plus, and then it's negative 4 times 2. 2 times negative 10 is negative 20. Negative 4 times 2 is negative 8. So this is negative 28. So these are fairly straightforward when they're in the Cartesian form. When they're not in Cartesian form, it becomes a little bit easier if you actually draw what's going on. So let's say that you had two vectors here, and you didn't know the Cartesian components, and you didn't feel like really doing them. But you know that one of them is, let's see, so let's say you know that you have two vectors here. One of them is directed this way, and one of them is directed this way. And there is, let's call that a 30-degree angle between the two. And let's make the length of this one 6 meters. Let's make the length of this one 5 meters. Something like that. Well, we can actually do a dot product without having to convert these into x and y components. We actually need to do very little trigonometry here, because there's a cheater way of doing a dot product. And that is this. If you have, I don't know, first vector here, let's call this M vector. Let's call this N vector. So if you have these two vectors, and you want to find their dot product, M vector dot product N vector. If all you have is a diagram sort of like this, it's actually very simple in order to find it. You can prove using trigonometry. I'm not going to prove it to you today, but you can prove using trigonometry that the dot product is actually going to be the magnitude of M times the magnitude of N times the cosine of the angle between them. Now, this is kind of a funky looking thing. These absolute value things, these mean magnitude when we apply them to vectors. And magnitude means the length or the strength. So don't even worry about what direction they are. Don't worry about positives or negatives. Just give me how big these things are. And then we'll multiply them times the cosine of the angle between them. So in this case, it's going to be M is 6 meters times N is 5 meters times the cosine of the angle between them. Oh, and that happens to be 30 degrees. Remember, the angle between them, don't do this angle down here, don't do this angle up here. It has to be the angle between the two vectors. So it's that 30-degree angle between M and N. All right, this is equal to, I get 25.98, and let's round that to a 1. Our units, we have meters and meters, so this is going to turn into a meters squared. So that would be the dot product between those two vectors. It's actually fairly simple. It's pretty easy. Dot products are not very hard. Dot products are great. And why do we use dot products? Well, we use them when we are calculating, most importantly, things like work, which we will be getting to in Physics 1 in a few days here. If you're in Physics 2, you've already seen work. So a dot product is great because it gives you a scalar number. You'll notice there's no direction on this because this is a scalar. There's no direction. We don't have to worry about the direction of the final answer. However, sometimes we lose some important information by doing a dot product. That having been said, let's talk about cross products. All right, so a cross product is going to be a way of multiplying two vectors in order to get another vector. But before we get into cross products too much, we need to know one thing, and that is that cross products are, oops, wrong side of the pen. Cross products are inherently three-dimensional. That means it's not just x and y. We've got to worry about x, y, and z, the third dimension. Now, because cross products are inherently three-dimensional, we need to worry not just about the x direction and the y direction like we see here. We also need to worry about the z direction, which is going to be this way. A little bit harder to make an arrow here. Something like this, maybe? There we go. So now we have three arrows, one in the x, one in the y, and one in the z. How am I going to label that z? Boy, I'm going to have to think about that. So because cross products are three-dimensional, we're going to have to think about these in terms of x, y, and z. So you already saw that we had the I hat to represent the x direction. We had the j hat to represent the y direction. And you can probably guess the k hat is going to represent the z direction. So let's say you have two vectors. Your first vector, and let's call it vector A, is going to be equal to 3i hat plus 4j hat plus 5z hat. And maybe your second vector, B vector, is going to be equal to 2i hat plus 5j hat plus 10z hat. Okay, you could see we've already shown you how to do a dot product on these, and it would actually be pretty straightforward even with the three-dimensional. So if I do a dot product A, dot product B, all that would be is I would multiply 3 times 2 plus 4 times 5 plus 5 times 10. And I would get something like 3 times 2 is 6, 4 times 5 is 20, so that's 26 so far. 5 times 10 is 50, so this would be 76. But we're not doing a dot product here. We're not too concerned about this because we want to learn how to do a cross product. So in a cross product, here's what we're going to do. We're going to start by making a 3x3 matrix. Wait, what, Mr. Williamson? Okay, here's how you set it up. We're going to have I hat, j hat, and k hat. We're going to start with that first line every single time. Always. I hat, j hat, k hat. Then we're going to take each of these components. So under the I, we're going to put vector A in. We're going to put a 3 here because that has a 3 component for the x component. Under the j, we're going to put a 4, and under the k, we're going to put a 5. So it's each of those components from that first vector. Then in our third line, we're going to put each of the components from the second vector. So it's going to be 2, 5, and 10. Finally, we're going to show that we need to find the determinant of this matrix. In order to find the determinant of the matrix, we're going to use a method called minors. So from this, we're going to make 3 2x2 matrices. What do I mean by that? Well, here's what we're going to do. The first thing we're going to do is we're going to take out this I hat. So I'm going to say I hat. Then it's going to be multiplied times the determinant of a 2x2 matrix. And we're going to eliminate everything in the same row and same column. So you can see here that what we've got is this 4, 5, 5, 10 matrix that's left. So I'm going to write that minor down here as the determinant of 4, 5, 5, 10. All right, then we are going to subtract. And each of these pieces is going to alternate. So it's positive is the first one, negative is the second one, positive is the third one. So there's a minus sign there. And there's going to be right here, we're going to look at j hat now. And you can see if we eliminate the entire row and the entire column, we are left with 3, 5, 2, and 10. So it's going to be j hat. Oh, let me get rid of those lines. So minus j hat times the determinant of 3, 5, 3, 5, 2, 10. Plus, well, now we're going to go on to the third one. It's k hat. We're going to eliminate this and this. And you can see we have 3, 4, 2, 5. So 3, 4, 2, and 5. K hat times the determinant of 3, 4, 2, 5. Okay, so now how do you find the determinant of a 2x2 matrix? It's pretty easy to do. Here's what you do. It's this times this minus this times that. So multiply diagonally, going from top left to bottom right, minus top right to bottom left. So in this case, if I was to show this, this would be I hat times 4 times 10 minus 5 times 5. All right, the next component here, so minus j hat, and then again, multiply this way, minus multiply that way. So this is going to be 3 times 10 minus 5 times 2. And then plus k hat, and then it's going to be 3 times 5 minus 4 times 2. 3 times 5 minus 4 times 2. Now all we have to do is simplify this. So this is going to be I hat. Let's see, 4 times 10 is 40. 5 times 5 is 25. 40 minus 25 is 15. Minus, let's see here, we have 3 times 10 is 30. 5 times 2 is 10. 30 minus 10 is 20. Plus k hat. And then 3 times 5 is 15. 4 times 2 is 8. 15 minus 8 is 7. So if we were to write this, we would write A cross product B is equal to, I'm just going to rearrange this because usually the hats go on the end, 15 I hat, minus 20 j hat plus 7 k hat. And that is how you do a cross product in Cartesian form. Now it turns out that doing a cross product in Cartesian form gets a little bit tedious. It's a lot of work. It's not hard, it just takes a lot of steps. So because of that, we came up with a way to sort of cheat as we're doing this. And but in order to do that, I'm going to need to teach you how to draw a couple things. So let's call this to the right of the page. And let's call this Or maybe it's my screen, so to the right of the screen. Okay, this way is going to be called to the left of the page or screen. I'm going to call this way toward the top of the page or screen. And let's call this way toward the bottom of the page or screen. So those are pretty simple. You've probably seen all of those before. To the right, to the left, toward the top, toward the bottom. Why we're not calling them up and down is because it depends on the way your screen or your page is oriented. If you have a piece of paper in front of you, is up that way or is up that way? It's hard to tell based on that piece of paper. So don't say up. Say toward the top of the page or toward the bottom of the page. Finally, since this is three-dimensional, we need a way to draw that third dimension. And that is going to be like this. This is going to be into the page. And this is going to be out of the page. The way you remember that is if you think about an arrow. If an arrow is coming toward you, out of the page, you're going to see the tip, the arrowhead, and it's going to look like a point. On the back of the arrow, if the arrow is going away from you, if you just shot an arrow and it's going away from you, you're going to see the feathers on the back, or the fletching perhaps, on the back of the arrow. And so because of that, you see sort of this X-shaped. So into the page is an X, out of the page is a dot. Why is that important? Well, that's important if we need to multiply two vectors. And really, this cheater method works best when vectors are at 90 degrees to each other. Sometimes you can kind of sort of work with it if it's not, but your vectors really do need to be at 90 degrees to each other for it to work well. So let's imagine that we have one vector that is directed this way. Let's call this A. We have another vector that is directed this way. Let's call this B. And let's call this one, I don't know, 3, let's use the right colors. Let's call this one 3 meters long. And let's call this one, that looks like about 5 meters maybe. So here are my vectors A and B. And I want to find the cross product of A cross B. A cross B. So the cheater way of doing this, if I only care about how strong this is, I can figure out the magnitude of this thing. And that's going to be equal to the magnitude of A times the magnitude of B times the sine of the angle between them. So in this case, it's going to be 3 meters times 5 meters times the sine of, in this case, I already told you that was a 90-degree angle, so it's the sine of 90 degrees. This is nice because the sine of 90 degrees is 1. 3 times 5 is 15 times 1 is 15 meters squared. But there's one problem here, and that is this is supposed to give us a vector. And the problem is, using the cheater way, I've only gotten the magnitude of that vector. I only know how big it is. I don't know the direction. So, in order to figure out the direction here, I use what's called the right-hand rule. Here's how it works. We're going to take our index finger, and we're going to line it up in the direction of that first vector. So to me, as I'm looking at my screen, A is directed to my right, so I'm going to point... this camera's going the wrong way. Let's do this. All right. So I can see on my screen And let's expand that a little bit so you can see. All right, so I can see on my screen the A vector is pointed to the right. So I'm going to take my index finger, I'm going to point it straight out, and then I'm going to line it up with the direction that my first vector is pointing. To me, it's to the right, so it's going to go that way. Now, I'm going to take my second vector, and my second vector happens to be B. I'm going to make sure I have a 90-degree angle between my two fingers, and I'm going to sort of rotate this so my first finger stays with A, so it's got to be that way, and my second vector has to be B, which is this way, straight up, toward the top of the screen. Now that I have that, I can use my thumb. If I extend that 90 degrees, it will tell me which way my third vector is going to go, my resultant vector. When I do a cross product on A and B, my thumb points in the direction of the product. And you can see here, my thumb is pointing out of the screen. So it turns out that in this case, put this back up here, the direction of this, and let's shrink this down again. That's about right. That's probably too high. All right, so turns out that the direction of this thing, when we look at this, is going to be out of the screen. So 15 meters squared out of the screen. We could verify this by doing this the long way. In fact, that might be a great thing for a student to do. What would happen if we had this in Cartesian form? Well, here's what we would do. We would start by writing a 3x3 matrix with I, J, and K. In the first vector is just A. It's in, I'm going to call that way X. I'm going to call that way Y. And I'm going to call out of the screen Z. And if I do that, the first one, A, is 3 meters in the X direction and nothing else. The second one is 5 meters in the Y direction and nothing else. So this is going to be equal to, if we find the determinant of this matrix, it's going to be I hat times the determinant of, let's see, it's 0, 0, 5, and 0, minus J hat times the determinant of, it's going to be 3, 0, 0, 0, plus the determinant of, K hat, determinant of, it's going to be 3, 0, 0, 5. 3, 0, 0, 5. And you can see we're going to end up with, multiply that, that's 0, multiply that, that's 0, so 0 I hat. Here again, multiply that, that's 0, multiply that, that's 0, so minus 0 J hat, plus 5 times 3 is 15, minus 0 is 15 K hat. So it turns out A cross B is equal to this vector, no I, no J, and only 15 K hat, which is exactly the same as saying 15 out of the screen, because we said that way is the Z direction. So that's really all there is to it as far as cross products and dot products go. These are going to be important in some of the lessons that are coming up in the future. In AP Physics 1, dot products are all over the place and work. And then torque is going to be a cross product. And rotational motion in general uses a lot of cross products. In Physics 2, we're going to see cross products come up as we start to get into the mathematics of magnetism. So it's important that we have a good understanding of the fundamentals of how to multiply vectors. Mahalo for watching, and see you next time.